Welcome to the deep dive. Today we're cracking open the blueprints of large language models, those AI powerhouses changing how we interact with everything. Think of this as your shortcut to understanding what really makes them tick.
Exactly.
Why should you, the learner, care? Well, grasping these inner workings reveals not just what these AI can do, but also their limits, which is crucial whether you're prepping for a meeting, trying to get up to speed, or just curious about the AI you use every day.
It really is. It's about moving past the sort of magic feeling and understanding the actual machinery.
Mhm.
And we'll be focusing today on the two main architectural styles, right?
Right.
Autoregressive, or AR, models, they're the established players, and then diffusion models, which are, well, they're rapidly advancing challengers,
Yeah.
especially after their big successes in image and audio.
Yeah, AR models like the GPT series, they've really set the stage for what we expect from language AI. But diffusion models, they're like this rising tide, bringing a totally different way of generating stuff.
And that's what's so interesting, isn't it? This shift. AR models have been, king of the hill for so long. But the unique strengths of diffusion models, their whole different approach to creation, that's sparking a ton of excitement, a ton of research in the text world now.
So our mission today, demystify these architectures. We want to unpack their core ideas, look at their strengths, their weaknesses, all in a way that's clear, hopefully engaging, and doesn't drown us in jargon. Ready?
Absolutely.
Yeah.
Let's start with the paradigm that's been the workhorse for, well, for years now, autoregressive LLMs.
Okay, autoregressive LLMs, let's break it down. The core idea seems to be predicting the next piece, right? One step at a time. Like building with Legos. Each new block depends on what you've already built. Is that kind of how AR models make text word by word?
Precisely. For any sentence, the model figures out the probability of every possible next word based entirely on the words that came before it. It's sequential, very much like how we often think when we speak or write. And the math behind it, you mentioned the chain rule of probability earlier. It essentially breaks down the chance of the whole sequence happening into the chances of each word following the previous ones. That sequential dependency, that's the absolute key.
And the engine running these modern AR models,
Yeah.
that's mainly the decoder-only transformer architecture.
Yeah, that's the one. And within that, a really critical piece is the self-attention mechanism.
Self-attention.
Yeah, what's clever here is how, when it's predicting that next word, the model doesn't just treat all the previous words the same. It dynamically figures out how relevant each past word is,
Ah.
which ones are most important for discussing what comes next. That's how it grabs onto those long-range connections, the subtle stuff that makes language make sense. It's a big reason they generate such fluent text.
So it's like the model has this internal spotlight
Yeah.
focusing on the most relevant bits of what it just said to decide the next bit.
Exactly. And then there's causal masking. This is absolutely fundamental for autoregressive generation.
Causal masking. Why is
Mhm.
that so important?
Because the model has to predict the next word. Causal masking physically stops it from peeking ahead in the sequence. It ensures that when predicting, say, word 5, it can only look at words 1 through 4, not 6, 7, 8.
Okay.
It forces the model to learn genuine dependencies in the language. It can't just cheat and copy the answer it's supposed to be predicting. It's a core constraint. It has to learn to generate.
Right. Like trying to finish a jigsaw puzzle, but you can only see the pieces you've already put down. You have to figure out what fits based only on what's already there.
Yeah.
Makes sense. What else is in this transformer toolkit?
Well, we also have positional encoding. Because transformers, they kind of look at all the words in a sequence at once, in parallel.
Yeah.
So they don't inherently know the order.
Right.
Positional encodings are like adding a little label or timestamp to each word saying you're first, you're second, etc.
Yeah.
Crucial because word order changes meaning completely, obviously.
Yeah.
Then there's multi-head attention. Think of this as the model looking at the relationships between words from several different perspectives, all at the same time.
So not just one way to see connections, but multiple angles analyzed simultaneously.
Got it. And you mentioned feed-forward networks, layer norm, residual connections. How do they fit in?
So those are really important building blocks for deep learning in general. They help these huge transformer models train effectively, help stabilize things, allow information to flow better through many layers, basically let the model learn really complex patterns. They're vital for making AR LLMs powerful and reliable, but maybe less directly tied to the autoregressive part itself compared to, say, causal masking.
Okay, so they're essential plumbing, but maybe not the core principle of AR itself. These architectures sound incredibly complex. Can you give us a concrete example just to grasp the scale?
Oh, absolutely. Take GTT3, a well-known one, the biggest version. It has 96 of these transformer decoder layers stacked up.
96 layers.
Yeah, and each layer has 96 attention heads. It all adds up to, well, an incredible 175 billion parameters.
Billion.
Billion. Those are the knobs the model learns during training. And it can handle input sequences, context windows, of over 2,000 tokens. That scale gives you a sense of the sheer complexity and power these AR models have.
175 billion knobs. Wow, that really puts it in perspective. And you mentioned variations, too. It's not just one single AR design.
No, definitely not. The field keeps pushing. For instance, some models use hierarchical structures, trying to process info at different levels, like paragraphs versus sentences. Others play with character-level processing, dealing with individual letters. That can be good for weird words or different languages. It shows there's still a lot of innovation happening even within this established AR approach.
Okay, so that's the structure. How do they actually learn? What's the training process like?
Training really centers on causal language modeling. Basically, you show the model tons and tons of text, and its job over and over is just predict the next word in the sequence.
Just predict the next word.
Yep. It sees the cat sat on the, and it has to predict Matt. It does this billions of times on massive data sets. And how does it know if it's getting it right or wrong?
That's where the cross-entropy loss function comes in. At each step, the model gives a probability score for every word in its vocabulary, possibly being the next one. The loss measures how far off that prediction is from the actual next word in the training data.
Ah, okay.
The whole goal of training is to tweak those billions of parameters to minimize this loss, to make its predictions match the real text as closely as possible.
So it's constantly adjusting itself based on feedback, trying to get better at that next word prediction game across all the text it sees.
Exactly. And during training, there's a common technique called teacher forcing.
Teacher forcing.
Yeah. When the model is learning to predict, say, word 5, instead of feeding it its own prediction for word 4, which might have been wrong, you feed it the correct word 4 from the training data.
Okay. Like giving it the right answer for the previous step to help it learn the current step.
Right. It helps stabilize learning, stops errors from compounding too badly during training. But, and this is important, it's different from how the model generates text later, right? During actual generation, or inference, it has to use its own previous outputs.
Right. It doesn't have the teacher anymore. It's on its own. That makes sense. And the data sets, it's really massive.
Oh, unbelievably so. We're talking terabytes of text. Books, articles, websites, code, conversations, you name it. It needs that sheer volume to learn all the subtle patterns and knowledge embedded in human language.
Okay, so the model's trained. It's learned from this mountain of data. Now, the exciting part, how does it actually generate new text?
So during inference, which is just the fancy word for generation, AR models basically keep doing that same core thing, predicting the next token in the sequence.
So still next word prediction, but now it's building something fresh, not just mimicking the training data.
Exactly. You usually give it a starting point, a prompt. It could be a question, a sentence fragment, or sometimes just a special start signal. It predicts the most likely next token, adds that to the sequence it has so far, then uses that new, longer sequence to predict the next token, and on,
Step by step.
token by token, until it hits some length limit you set, or it predicts a special end token.
And at each step, it's calculating probabilities for all the possible next words.
Yes. Its output is a probability distribution across its entire vocabulary. Thousands, maybe tens of thousands of words, each with a likelihood score. And how we choose the actual word from that list, the decoding strategy that dramatically changes the kind of text you get.
Ah, yes, decoding strategies. This feels like where we get some control over the output, right? The creativity versus predictability balance.
Absolutely. This is a really key part. The simplest way is greedy decoding.
Greedy. Sounds simple.
It is. You just always pick the single word with the highest probability score. That's it. Fast, easy, but it often leads to really repetitive, boring, sometimes nonsensical text. It gets stuck in loops easily because it never explores, slightly less probable, but maybe better long-term option.
Well, always playing it safe, which isn't always the best strategy in language. Okay, what else?
Then there's beam search. Instead of just following the single best path, beam search keeps track of, say, the top 3 or top 5 most likely sequences or beams at each step.
Okay.
It explores extending each of these beams, calculates the probabilities, and keeps the best few overall sequences. It generally gives better quality, More coherent text than greedy because it looks ahead a bit more, but it can still lack diversity, often favoring very common, predictable phrasing.
A bit more exploratory than greedy, but still maybe not super creative. Now, I know there are ways to inject more randomness, right, for more interesting results.
Yes, exactly. Those are the sampling strategies. They introduce randomness. A
Mm.
really common one is temperature scaling.
Temperature, like turning up the heat.
Kind of. You use a temperature value to adjust the probability distribution. Higher temperature flattens the probabilities, making less likely words more likely to be chosen. More randomness, more surprise, potentially more creativity.
But maybe more errors, too?
That's the trade-off. Lower temperature makes the distribution sharper, more like greedy search, more focused on the most probable words. So you tune the temperature to find a balance between coherent and creative.
Okay, that makes sense. Adjusting the creative heat, what other sampling methods are there?
There's top K sampling. Here, you just ignore all words except the most probable ones. So maybe you only consider the top 50 words. Then you redistribute the probabilities among just those top 50 and randomly pick one from that smaller set.
So it narrows a field first, then picks randomly from the likely candidate.
Right. It avoids picking really weird, low probability words, but still gives you diversity within the reasonable choices. And similar, but maybe more adaptive, is top hour or nucleus sampling. Instead of a fixed number K, you select the smallest group of top words whose probabilities add up to a certain threshold, P to maybe 90% or 95%.
Ah, so the number of choices can change.
Exactly. If the model is really confident about one word, high probability, the nucleus might be very small, maybe just one or two words. If the model is uncertain, probabilities are more spread out, the nucleus will be larger, giving more options. Then you sample from within that nucleus.
That sounds clever. More flexible.
It is. And there are newer ones too, like min sampling, which tries to strike an even better balance, especially when using higher temperatures. Long story short, the decoding strategy you pick, hugely important for the final output.
Definitely sounds like a key control knob. Now, generating text token by token sounds like it could get slow, especially for long pieces. Is there anything that helps speed that up?
Yes, absolutely crucial is KV caching. Remember, the self-attention mechanism looks back at previous words. It calculates representations called key, K, and value V vectors for those words. When you generate the next word, the K and V vectors for all the previous words haven't changed. You don't need to recalculate them from scratch. KV caching stores or caches these vectors. So, for each new token, you only compute the K and V for the current token and reuse the cached ones. It massively speeds up inference.
Ah, so it's like short-term memory for those attention calculations. Avoids redoing the same work over and over. Makes total sense for efficiency. Okay, so we've dug into how AR models work. Let's sum up. What are their defining hallmarks, their big strengths and weaknesses?
Okay, strengths first. They are really good at producing coherent and fluent text. That sequential, context-aware generation really pays off there. They show strong semantic understanding, at least within the context they're building. And importantly, the whole AR approach, especially with transformers, is well established and very scalable. We know how to build bigger ones and generally make them better.
Those are big pluses, why they've been so dominant. But the weaknesses, we touched on some.
Yeah, definitely weaknesses too. A big one is arrow propagation. One bad word choice early on can throw off everything that follows because that error becomes part of the context.
Right, the mistake snowballs.
Exactly. Then there's the sequential bottleneck and the inference cost. Even with KV caching, generating one token after another takes time. It's inherently serial. A fundamental one is the unidirectional limitation. Only looking backwards, never forwards, can limit its grasp of the full picture sometimes. They're also prone to hallucinations, making stuff up that sounds plausible but isn't true.
Yeah, we've all seen that.
And with deterministic decoding, they can lack diversity. Finally, dealing with really, really long inputs can be tough, computationally expensive, memory hungry, and sometimes the model loses track of information from way back at the start.
That unidirectional thing does feel like a core limitation, doesn't it? Like trying to write a story, but you can only see the sentence you just wrote, not the overall plot outline.
That's a good analogy. And that limitation, along with others, is exactly why researchers started looking seriously at different approaches, which brings us nicely to the challenger. Diffusion models for text.
All right, diffusion models. We hear about them a lot for images, generating amazing pictures. How does that idea translate to text? What's the core concept?
Okay, so the core idea is quite different. It's this iterative dance of noising and denoising, gradual refinement. Instead of predicting the next word directly, Diffusion models usually work in two
Two
phases.
phases. Okay.
First, you take the clean original text and deliberately add noise to it, step by step, progressively scrambling it until it's, well, mostly noise. Then the second phase is where the trained model comes in. It starts with that noisy data and learns to reverse the process, iteratively removing the noise step by step to get back to the original clean text or to generate new text.
So like taking a clear photo, blurring it out completely, and then training an AI to unblur it back into a sharp image.
That's a great analogy for the image domain, yeah. For text, think of it maybe like taking a finished sculpture, covering it in clay bit by bit until it's just a lump, and then teaching another sculptor to carefully remove the excess clay step by step to reveal the original form again.
Okay, gradual destruction, then gradual reconstruction. But text is different, right? It's discrete things, words, tokens, images are continuous pixels. How does diffusion handle that jump?
That is the crucial challenge, and where the adaptation gets clever and also tricky. Early diffusion models work beautifully on continuous data like image pixels or audio waveforms. Text is fundamentally discrete. So researchers came up with two main strategies.
Strategy one.
Continuous diffusion in embedding space. So first, you turn the discrete text tokens into continuous vectors word embeddings. Think of placing each word as a point in some high-dimensional space. Then you add the standard kind of noise, Gaussian noise usually, to those vector positions, just like you would to image pixels. The model learns to denoise these noisy vectors, and the final step is mapping those denoised vectors back to the nearest actual discrete word token.
So map words to points, jiggle the points randomly, unjiggle them, then snap back to the closest word. Does that work well?
It can work. Models like Diffusion LLM use this. But that final step, mapping back from the continuous vector to a discrete token, can sometimes lose information or introduce errors. It's not always a perfect mapping.
Right, the vector might end up in a space between valid words. What's the other strategy?
The other way is discrete diffusion directly on tokens. Here, the noise is applied straight to the tokens themselves.
How do you add noise to a word directly? Change letters.
Sort of. It's defined by transition probabilities. You set rules for how likely a token is to change into another specific token at each noising step. So a word might have a small chance of flipping to a random other word, or maybe a chance of being replaced by a special mask token, which kind of links to how we sometimes prompt AR models. Or more complex rules try to mimic continuous noise or make transitions more likely between semantically similar words.
So instead of continuous blurring, it's like words randomly mutating or getting blanked out according to set rules.
Exactly. Different models like D3PM or SEDD use various forms of these discrete corruption processes. Designing these transition rules effectively is a really active area of research. It's much less straightforward than just adding Gaussian noise.
Sounds like it. Now, the architecture. You said diffusion models often use transformers too.
Yes, the transformer architecture often serves as the denoiser network, the core engine that learns to remove the noise at each step.
So transformers are versatile, but is it the same kind of transformer as in AR models?
Here's a key difference. The transformer used in diffusion models typically employs bidirectional self-attention.
Bidirectional, not causal.
Right. Remember, AR models use causal masking, only looking backwards. Diffusion denoisers often look at the entire noisy sequence at each step, both forwards and backwards. This gives them a global view, a sense of a whole context, even when it's noisy, at every single refinement stage.
That sounds like a big advantage. It can see the whole blurry picture to figure out how to clarify it, not just the bit that came before.
Precisely. It allows for potentially better global planning and understanding of relationships across the whole sequence, which is fundamentally different from the left-to-right AR process.
Okay, so how does training work for these, and then the generation, the inference?
Training involves taking clean text, adding noise according to a predefined noise schedule, which dictates how much noise is added at each of the many time steps, and then training the transformer denoiser to predict either the original clean text or sometimes to predict the noise that was added.
That noise schedule sounds important.
It's critical, controls the whole process. And as I mentioned briefly, people are even looking at hyperschedules, where different parts of the sequence might get noise added differently. Lots of flexibility there.
And then to generate new text, inference.
You start with pure noise, essentially a random sequence, or maybe a fully masked sequence. Then you apply the trained denoiser model iteratively over many steps, gradually removing the noise or filling in the masks.
Step-by-step refinement.
Exactly. And the number of denoising steps, the NFEs, is a big factor. More steps generally means better quality output. but it also takes longer. It's a classic quality versus speed trade-off.
More steps, more refinement, better text, but slower.
Got it. So what's the potential upside here? What are the strengths that make people excited about text diffusion? Well, the potential strengths are really compelling. One big one is generation diversity. Because you start from random noise and the denoising is stochastic, they tend to produce more varied outputs naturally.
More variety, less repetition.
Exactly. Another is controllability. The iterative process offers many points where you can inject guidance or constraints. You can condition the denoising based on desired attributes, styles, keywords. It seems inherently more flexible for control.
Multiple chances to steer the generation.
Right. There's also the potential for parallel generation within each step, which could eventually lead to high throughput on the right hardware, though maybe not low latency yet. The global planning ability from bidirectional attention is a theoretical plus. And finally, that iterative refinement offers self-correction potential. An error made early on might be fixed in later denoising steps.
Those sound like really significant advantages. Diversity, control, self-correction, but what about the downsides, the hurdles?
The biggest one right now is computational cost and infinite speed. Running that denoiser potentially hundreds or thousands of times is just slow compared to a single-pass AR model. That's the major barrier.
Speed, yeah.
Then there's the complexity in handling discrete data, getting the embeddings right, or designing those discrete transition rules. It's tricky. Coherence and overall text quality, while improving rapidly, can still sometimes lag behind the best AR models, especially for very long, intricate text. And the training complexity can also be higher.
So lots of exciting potential, but still some big challenges, especially on the efficiency front, before they completely take over.
That's a pretty fair summary of where things stand.
Yeah.
But this comparison leads to a really fascinating idea. Are AR and diffusion models truly separate species? Or maybe more like cousins?
Oh, you're suggesting there might be a deeper connection, that these two different ways of generating text are related somehow.
Exactly. There's some really interesting theoretical work emerging that suggests actually autoregressive models can be seen as a specific, maybe degenerate form of discrete diffusion.
Wait, hold on. Generating one word after another, how is that like adding noise and removing it? Where's the noise?
Okay, think about it this way. When an AR model is about to predict, say, the 10th word in a sequence, you can think of all the words after position 10 as being in a state of maximum noise. They are completely unknown, effectively masked.
Okay. Future tokens are the noise.
Right. The AR generation process then denoises exactly one position at a time in a fixed order, left to right, by predicting and revealing the token for that position.
So the noising isn't gradual blurring, it's just binary. Either the word is known or it's completely masked, completely unknown.
Precisely. And the noise schedule is also binary, fully masked max noise, or fully revealed.
No noise.
There are no intermediate fuzzy states like in standard diffusion. The AR generation process is just one very specific deterministic denoising path, unmasking one token at a time sequentially. It operates without that gradual stochastic noise applied across the whole sequence.
Wow, that reframes it completely. So maybe not two totally separate boxes, but different points on a spectrum of how you reveal information.
Exactly. And thinking about it that way has big implications. It suggests a continuum. It also gives more context to that idea of hyperschedules we mentioned with diffusion.
Right, different noise schedules for different parts.
Well, hyperschedules generalize this. Standard AR, unmasking one token left to right, is one hyperschedule. Standard diffusion, gradually refining all tokens together, is another. But you could imagine schedules in between. Maybe you unmask blocks of text or use a sliding window. Hyperschedules open up this whole design space to blend AR and diffusion properties.
That's fascinating. So we could design models that maybe start AR-like for structure, then use diffusion-like refinement for detail.
Potentially, yes. And seeing this connection encourages cross-pollination. Ideas from diffusion like sophisticated noise schedules might inspire better sampling methods for AR models. Efficiency tricks from AR, like KV caching, might find uses in certain diffusion setups. It gives us a more unified way to think about generating sequences.
So it's not just a neat theory, it could actually lead to better, more flexible models down the line.
Okay, with that unified view, let's do a head-to-head. How do AR and diffusion stack up on practical LLM tasks?
Right, the practical side. So the generation process difference is still key. Sequential AR versus iterative diffusion. This leads to different output characteristics.
Okay.
Coherence. AR generally still has the edge, though diffusion is catching up fast. Diversity. Diffusion usually wins here. It's inherently more varied. Accuracy, factuality, both hallucinate, unfortunately. Diffusion's self-correction is a potential advantage, but not a guarantee yet.
And the crucial one, computational cost.
Training. Both expensive at large scale.
Yeah.
Inference latency, time for one output. AR is tied to length, diffusion tied to steps. Diffusion usually slower currently, though models like LLDA or Mercury are working on this,
Throughput.
doing many outputs at once. Diffusion's parallelism might give it an edge here with the right hardware.
What about steering the output? Controllability. Diffusion seems to have more built-in levers for control right now. Conditioning, guidance during the steps. AR control is mainly via the prompt and fine-tuning.
And handling mistakes. Robustness.
Diffusion's iterative nature gives it that potential to recover from early stumbles. AR errors tend to stick around and compound.
And just building bigger, better versions. Scalability.
AR has a proven track record here. Diffusion for text is newer, but early signs for scaling are promising too.
So it really feels like a trade-off, doesn't it? If you need rock-solid coherence and speed today, AR might be your best bet. But if you need diversity, fine-grained control, and believe the speed issues will be solved, diffusion is incredibly promising.
That's a great summary. It's not about which is universally better, but which fits the need. And this naturally leads us to the frontier. Hybrid models and where things might go next.
So the future isn't necessarily AR or diffusion, but maybe AR and diffusion, combining them.
That seems to be a major trend. We're seeing a lot of excitement around hybrid models that try to get the best of both worlds.
How does that work in practice? What do these hybrids look like?
Well, one idea is using strong AR models to guide diffusion. Maybe the AR model generates a high-level plan or summary, and the diffusion model uses that as a condition to fill in the details.
AR for the structure, diffusion for the texture.
Kind of like that, yeah. Or using diffusion ideas like noise during AR training or sampling to boost diversity. We're seeing LLMs being used as controllers for diffusion processes, leveraging the LLM's semantic understanding to steer the diffusion. There's even work like diffusion of thought, trying to integrate diffusion with chain of thought reasoning.
These sound really powerful, potentially, but we keep coming back to the diffusion efficiency problem. What's being done to make them faster?
That is priority number one for practical use. Huge effort is going into faster sampling, finding ways to get good results with way fewer denoising steps, using better math, smarter scheduling, non-Markovian approaches. Also model compression, making the denoiser itself smaller and faster through techniques like distillation or quantization. And, of course, hardware acceleration designing chips optimized for these kinds of computations.
So, attacking the speed problem from multiple angles. Fewer steps, smaller models, faster chips. Makes sense. Beyond speed, what other big challenges are researchers tackling for diffusion?
Refining controllability further is key, making it easier to get exactly the output you want. Really mastering discrete diffusion is still ongoing, finding the best ways to handle tokens directly for top-tier quality, and just continuing to push coherence to match or exceed AR models consistently.
Okay, so looking ahead, say, 5 years, what do you think the LLM architecture landscape looks like?
My guess. Continued exploration of that whole AR diffusion spectrum. More sophisticated hybrid models will become common. We'll likely see more specialization architectures fine-tuned for specific tasks, maybe dialogue versus summarization versus coding. Hopefully, more focus on interpretability, understanding why models say what they say. Architectures built for continual learning, so they can adapt without full retraining, will be crucial. And while transformers dominate now, maybe we'll even see serious contenders emerge from non-transformer backbones. It's all moving towards more capable, reliable, controllable, and efficient LLMs.
This has been incredibly insightful, a real deep dive into the engine room of modern AI. So for you, the learner, the big takeaway, autoregressive models have been the champs, great for coherence. Diffusion models bring exciting new things like diversity and control, and the future. Probably a mix, these hybrid approaches.
Exactly. And remember, there's no single best architecture. It always depends on what you need that AI to do. What are your goals for it?
And like we said, this field moves incredibly fast. Keeping tabs on these architectural shifts is really key to understanding where AI is going. So maybe a final thought for you to chew on. Think about the AI you use now, or the AI you dream of building. Which of these strengths and weaknesses we talked about, coherence versus diversity, speed versus control, which are the most critical for those applications? Pondering those trade-offs is going to be vital as you navigate the future of language AI. Thanks for joining us on this deep dive.